Hello, everybody. My name is Marwan Galai.
I'm Julia Oppenheimer.
And I'm Cody Corey.
Our project is the Unmanned Ground Vehicle for simulating unmanned air vehicle landing. Our industry sponsor is Mr. Alex Lorman, and our faculty advisor is Professor Cheng Cao.
Our sponsor is TheraMahan, a company located in Groton, Connecticut that specializes in autonomous maritime surveillance. They were experiencing a problem of being unable to retrieve their unmanned air vehicles after they were sent out on water missions. Each UAV the company loses costs between $10,000 and $80,000. TheraMahan's solution is to have the ability to autonomously land the UAVs on boats out in the ocean, but they need to develop the landing method before attempting it over water. Our team's job was to design and create a prototype unmanned ground vehicle that is able to communicate its location to a UAV so the UAV can practice autonomously landing on a moving target over dry ground. The UGV's requirements are listed on the right. Our final prototype consists of a plywood chassis with the electronic components mounted directly to its surface. 2 caster wheels are mounted in the front for ease of turning, and 2 10-inch pneumatic wheels are mounted in the rear, each attached to a DC motor. The motors are then attached to the chassis with our 3D printed motor brackets. A netted landing platform is suspended above the chassis to prevent the UAV from damaging the electronics after it lands. Legs, designed by Team ME55, will be attached underneath the UAV and are shown here to the right. As the UAV lands, the legs will poke through the net suspended above the platform, which will prevent the UAV from sliding off the UGV as it continues to move.
Here are 4 components that help secure the rear wheels to the unmanned ground vehicle. These components comprise of 10-inch pneumatic wheels themselves, motor hubs, DC motors, and 3D printed motor brackets, which are attached to the chassis base through the use of bolts. A drive axle is fitted through each of these components to help attach them all together. As you can see, here is an underside view of the unmanned ground vehicle. In orange is the 3D printed motor bracket. Here is the drive axle, which is bolted in place with the use of a bottom plate, which helps clamp the axle to prevent it from moving. On the left, you can see that the motor is bolted to the bracket to help increase its stability and security to the vehicle. For our front wheels, we use caster wheels, which help enable a tighter turning radius as well as a smoother turn for the ease of maneuverability, as you can see in this video.
This is an ANSYS simulation we did on our motor hub. Our motor hub is connected to the wheel at 4 different points via bolts here, 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 and there. And the wheel is going to produce a torque onto the motor hub of 22.2 pound-force inches, which is derived from the specs from the motors that we chose. If you look in the bottom left, you can see a shear analysis we ran on the motor hub in ANSYS. The max shear stress from the simulation is calculated to be approximately 465 psi, and the max shear strength of polyethylene is known to be 4800 psi. So from the simulation, we know that there's no chance of shear failure. Moving right, we can see the von Mises stress of the part is 1202 psi here, and that the ultimate stress of the material is 1653 psi. This gives us a factor of safety of 1.37, which in this environment is a suitable enough factor of safety. Here on the left is a general motion test we did on our vehicle to see how it drove. In this this was a earlier prototype that we had made, and we were just seeing how it moved and how it handled. On the right, you can see a table of the results we did of 3 different velocity tests. We got an average of 26.53 seconds for the UGV to travel 270 feet. That calculates to about 10.18 feet per second, which is above our required velocity of 6.5 feet per second. In summary, our UGV is constructed primarily out of plywood with front caster wheels used for steering. There's 2 DC motors in the rear that are used to drive the vehicle at approximately 10 feet per second, which is faster than our 6.5 feet per second requirement. We have a netted platform that is above the electronics, which is used to prevent the UAV from shifting while the UGV is in transit. Next steps for the project are to secure the RTK GPS to the chassis, enable location communication between the UGV and the UAV, and autonomously land the UAV on top of the UGV. Thank you for watching.